All right, let's look at our sample test for sections 410, 5.1 to 5.5. Now, I know it says to 5.7 up here at the top, but it is just through 5.5. That's why you had a couple of problems that you omitted on this one. So number one was one of the ones that you omitted, not because we haven't done it, but just because if you do one problem using Riemann sums, then obviously you could do two, and those are kind of time consuming and tedious. So let's look at number two. So for number two, first off, I need my change in x. So change in x is just b minus a over n. B is my upper limit and A is my lower limit of integration. So we can say 7 minus 2. And then they told us that n was equal to 5. And so we'll divide that by 5 and we find out that each subinterval is 1 unit long. So we're going to start at positive 2, and the first interval is going to go from 2 to 3, and then the next one from 3 to 4, and the next one from 4 to 5, 5 to 6, and 6 to 7. Now, because they told us to use midpoints, we're going to use the value that is the midpoint of each interval. So halfway between 2 and 3 is 2.5. And you can use a decimal or a fraction there. So you can see 2.5, 3.5, 4.5, 5.5, and 6.5 will be my midpoints. So to find the midpoint, the midpoint rule, we are going to use the change in x, which for us was 1, times f of the first midpoint plus f of the second midpoint plus f of the third one, the fourth one, all the way to the last one. Now, when we say f of 2.5, that means take 2.5 and plug it into the function. So our function was 1 plus x squared. So we're going to say 1 plus 2.5 squared. So 1 plus 2.5 squared would give me 7.25. And then we're going to do the same thing with 3.5. We're going to plug it in for x, and we would have 1 plus 3.5 squared, and then 1 plus 4.5 squared. So that's where these numbers are coming from. I add all of those up, and then I multiply it by my change in x, and that gives me my Riemann sum, or my approximation of the area under the curve using 5 midpoints. All right, then number 3, anytime your A and B values are the same, your answer is automatically going to be 0. There is no area that's being enclosed. For number 4, we have a piecewise defined function. And for every piecewise, you're going to break it up into separate intervals where each piece has its own interval. So for the first piece, it's going from 0 to 1, and it uses the function x cubed. So we're going to go from 0 to 1 with x cubed. And then the second piece goes from 1 to 3 and uses the function x squared. So for the second piece, we're going from 1 to 3 using x squared. Now you can treat those literally like two separate problems. If I were just working this first one out, I would say the antiderivative of x cubed is add 1 to the exponent, so x to the 4th, and then divide by that same number. So I've done the antiderivative, but I haven't plugged in my a and b values yet, so I'm going to leave them sitting over here to remind me to plug them in. Same thing for the second piece, add 1 to x squared and we get x cubed, and divide by that same number, and we've got our numbers there to remind us to plug them in. So when we go to plug these in, we're going to do b minus a. So if I plug in 1, I get 1/4, minus if I plug in 0, I get 0. So my first piece is going to be 1/4. All right, then my second piece over here, if I plug in 3, that's going to be 27 divided by 3, which is 9. And if I plug in 1, I'm going to get 1/3. So if I have 1/4 plus 9 minus 1/3, that's going to be 8 and 11/12. Now, on the review homework, you had to give the exact value on your definite integrals because we were doing these by hand, not putting them in the calculator. On the test, because you won't have your calculator on this page, you have a scientific, not a graphing, it's perfectly fine for you to give your answer as a decimal approximation. All right, then for number 5, do not make this problem harder than it is. I literally put a note on the test that says, do not make this problem harder than it is. So for this guy, the area under the curve from 0 to 4 plus the area under the curve from 4 to 6 would be the same as the area under the curve from 0 to 6. They're going to give me 2 of those 3 pieces, so I'm just going to plug in the 2 they gave me. They told me that from 0 to 4 it was -5, and from 0 to 6 it was 3. So all I have to do is say -5 plus what is equal to 3. If you want to replace this with an x, you could and say -5 plus x is equal to 3. So add 5 to both sides and you'll find out that your unknown is 8. All right, then for the next one, we have the sine of a quantity. You cannot take the sine of a quantity, so we're going to have to use u substitution. So I'm going to let u be equal to the quantity 4t. So the derivative of that is going to be 4. So the derivative is in terms of t, so the derivative is 4. And then we're going to find the differential by multiplying both sides by dt. So our differential du is going to be 4 dt. So if we come back over to our problem, then we can see that we're going to replace 4t with u. So that's going to be sine u. And the only thing that leaves me is dt, not 4 dt. So I've got to get rid of that 4. So the way that I get rid of that 4 is I'm just going to divide both sides by 4. So 1/4 du will be dt. So I've replaced 4t with u. I've replaced dt with 1/4 du. So I can pull that 1/4 out in front if I want to. But if I've switched all of these t's to u's, I also need to switch these t's to u's. So let's figure out when t is equal to pi over 4 what u would be. Okay, well u is 4 times t. So if t is pi over 4, that's just 4 times pi over 4. So 4 times pi over 4 is going to give me pi. And then the other value was 0. So if we plug in 0, 4 times 0 would be 0. So when t is 0, u is also going to be 0. So you can see that not only did our integrand get easier with the substitution, but also the values that we were using get simpler with our substitution. All right, so now we're ready to take the antiderivative. So the antiderivative of sine is negative cosine. And then we can plug in our pi and our 0. Now, I will give you a unit circle and a formula sheet with the derivatives and the integrals on it for the test. So you can just look on your circle and see that the cosine at pi is -1 and the cosine at 0 is +1. And then we're just simplifying our fractions there. So our area under the curve would be 1/2. All right, then for number 7, you have an absolute value. Every absolute value is going to be a piecewise defined function. So the first thing that I need to do is I need to redefine this where it's positive and negative. So I'm going to take 3x minus 2 and set it equal to 0 and solve it. And I find out that I have a root at 2/3. Okay, so now I need to figure out whether it's positive or negative on each side. So I'm going to pick a test point like 0. 0's over here. So if I take 0 and I plug it in, 3 times 0 minus 2 would give me a -2. So it's negative on this side of the root. Cross a single root, the sign changes. It's positive on that side of the root. So I'm going to divide that into 2 separate integrals. I'm going to start at -1, and I'm going to go from -1 to 2/3. Now from -1 to 2/3, it was negative there. So when I have the absolute value of something that's negative, I get the opposite of what I started with. So I'm going to get the opposite of 3x minus 2. Then from 2/3 on, which for us stops at +2, so from 2/3 to +2, the function is positive. So when what's inside my absolute value is positive, I get exactly what I started with. So you can see that I'm just going to use the regular function over here. Now we're back to normal integration again. So I'm going to say the antiderivative of 3x is 3x to the second over 2, and the antiderivative of 2 is 2x over 1. Same thing here, antiderivative of 3x is 3x squared over 2, antiderivative of negative 2 is negative 2x over 1. And then I can just plug in my values. So first I plugged in 2/3, and then I plugged in negative 1, and then I plugged in 2/3, and then I plugged in 2. All right. So when I get my two separate pieces, so here would be the answer for my first integral, that's 25 over 6. Here would be the answer for my second integral, that's 8 over 3. I'm going to add those two pieces together. So that gave me my final answer of 41 over 6. All right, then 8 was a problem that we omitted. So for number 9, when you notice that your values out in front are opposites of each other, the first thing you want to look for is whether this is even or odd. And the way that I check that is I put a negative x in the place of x. So if I put a negative x in the place of every one of my x's, I get negative x to the 5th plus a negative x, so minus x, over 3 plus negative x squared would just be positive x squared. If you'll notice, I could factor a negative out of my numerator. So I literally am getting the opposite of the exact same function that I started with. So if it's opposite, then it's odd. And remember that if you have your a and b values opposites of each other and your function is odd, your answer is automatically 0. All right, 10 was a problem we were omitting. So then for number 11, we are on the graphing calculator page now. So unless it tells you you have to work it by hand or you have to show work, you can just throw it straight into your graphing calculator. So if we're finding the average value of the function, then it's just the regular integration with 1 over b minus a out in front of it. So 0 is a and 3 is b. So we're just going to have 1 over 3 minus 0. So I know that's 1/3. And then this guy right here, I can just throw into my calculator. So I did work it out by hand just so that you would have another example of definite integration. But you want to do this on your calculator. So just a reminder of how we do that on our calculator. You could just do 1/3 right here if you want to. But to get our integral symbol, we're going to hit our math button and go down to function integrate. When I do that, it puts the blank definite integral on my screen for me so that I can plug in the 0, plug in the 3, plug in my function, and put my x right here. And when I hit enter, then it gives me that final answer. So we don't have to do any of this by hand. We're on the graphing calculator page. We can do it with our graphing calculator. The second part of that says find where the average value is equal to the function. So the average value I just got was 6, and I'm going to set that equal to my function. So my function was 6c minus c squared. So we're going to take the function and set it equal to 6. So I'm going to get it all on one side set equal to 0. So I added my c squared over here and I subtracted my 6c over here. So that gave me c squared minus 6c plus 6. Now that's a quadratic, so I can throw it in the quadratic in my calculator where a is equal to 1, b is equal to negative 6, and c is equal to positive 6. So when I do that, I get 3 plus or minus the square root of 3 from my calculator. 3 plus the square root of 3 is about 4.7. That's not in my interval. Whereas 3 minus the square root of 3 is in the interval between 0 and 3. So I want to give 3 minus the square root of 3 as my answer.